Thank you, Jörg, and the rest of the organizers for the kind invitation. I am going to talk about geometric Langlands, but clearly I should have gone before David's talk because I'm going to try to give a much more elementary, concrete approach to it without all the categories. So let's see, how does this work? Okay, so the goal of the talk is to explain a few aspects of geometric Langlands as it relates to homological mirror symmetry and Hitchin system, and especially non-abelian Hodge theory. I'll try to explain everything that's involved. So this is going to be joint work with Tony Pantev, and one crucial part is also joint work with Carlos Simpson. So let's start with what I consider to be the geometric Langlands conjecture, or at least the original version, before it started getting generalized. So it says that a geolocal system, let's call it V, on a Riemann surface C, gives, and in fact is equivalent to specifying an automorphic D module, we'll call it D sub V, on the moduli space of bundles. So these are bundles on C whose structure group is not G, but the Langlands dual of G. If you know what that is, you should be happy. If you don't know what that is, just take the case of GLN, and then it is self-dual. So GL is the Langlands dual, the thing that David was calling G-check. And it is uniquely characterized in terms of its character lattice. So the characters of G are the co-characters of the dual of the characters of its Langlands dual group. So it's hard to give a direct construction going from the group to its Langlands dual, but it's easy to specify the character lattice of the dual and use the classification of Lie groups to deduce the group from that. So as you know, there are much fancier versions of the conjecture, and one version would predict the existence of a canonical equivalence of categories between coherent sheaves on the moduli of local systems as opposed to D modules on BUN. So let's see. So you can have BUN, that means vector bundles, or a little more generally coherent sheaves, and then you take D modules on those, or you take a bigger space of local systems, but a smaller notion of function. You just want a function instead of a differential operator. And somewhere in here, there should be a G and a G dual. And this should be uniquely characterized by a rather mysterious property that says that this correspondence C should send structure sheaves of points on the local systems to Hecke eigen D modules on the other side. So that's quite a mouthful. Try to remember this formula, but I'm going to go back and explain it and motivate it and show what it says in some specific cases. Just for the notation, you have to choose an appropriate character. I'll call it mu. And then the Hecke character is actually filtered by finite dimensional pieces parameterized by those mu's. Okay, so let's really get started now. So the Langlands program is a non-abelian version of something that anyone who's had a first course in algebraic geometry would recognize. It's a non-abelian version of the Abel-Jacobi map. So when I say CFT, this is the inappropriate CFT for this conference. It's not conformal field theory, it's class field theory. My apologies. So the abelian case is well understood. It is just the theory of a curve, and it's Jacobian, the Abel-Jacobi map, relating them. So yeah, so in that case, it just says that if you have a rank 1 local system on the abelian variety, the Jacobian, you can restrict it or pull back. You get a rank 1 local system on the curve. And it says that this is an equivalence. In other words, every rank 1 local system on the curve extends to a unique local system, rank 1 local system on the Jacobian, whose restriction back to the curve is what you started with. So this is the abelian version. This is it follows right away from ideas of Abel and Jacobi. So in this case, the structure group is just C star, which is GL1. It's an abelian. That's why this is the abelian version. You'd like to extend that to more complicated groups. Let me just check something. Don't worry. Okay. Yeah. Let me just try to explain in words. I didn't write this down, but let me explain in words why this is actually true. The Abelianized version, the Abelian case of geometric Langlands. So you have a local system on the curve. You have a map from the curve to its Jacobian. What does it mean for it to extend? That means that there's a local system or a representation of the fundamental group of the Jacobian, which somehow pulls back to what you started with. The fundamental group of the Jacobian is just the Abelianization. It's H1 of the curve. It's the Abelianization. So in general, not every representation will factor through the homology. It will factor if and only if the representation is abelian. So that's why the abelian case just amounts to going from the fundamental group to the homology, or from the curve to its Jacobian, which is the Abelianization of the fundamental group. So there's a proof of the abelian case. So here's how we replace the key ideas from the abelian case by non-abelian ideas. So the Jacobian is replaced by Bunn, which is the moduli space, really should be the moduli stack, of principal bundles on the curve C, whose structure group is, well, on one side or the other, we need to put G dual. So I'm going to put G dual on this side. So Bunn would be the moduli space of G Langlands bundles. The analog of the Abel-Jacobi map is the Hecke correspondence. So if you remember the definition, the statement of the conjecture was that we're looking for eigensheaves of the Hecke operator. So here's what they are. So the Hecke correspondence is a subvariety or substack of Bunn cos C. It's a set of triples, so a bundle and another bundle and a point, satisfying a specific property. So in fact, I'm cheating a little bit. I'm going to make it the set of quadruples. So it's V prime and X, which is what I said, plus a beta, which is an isomorphism between V and V prime defined away from the point. So beta is described right here. Okay? But if you want to forget beta, you just say that it's a set of triples such that V prime is isomorphic to V except at the point. So it's obtained by some elementary modification or sequence of elementary modifications at this one point X, where the V and V prime are LG bundles and so on. Any questions so far? Okay. So just going back to the abelian case, so then G and GL are C star, and these are triples consisting of two line bundles, L and L prime, and a point X, where L prime is the only way you can modify is by tensoring with the line bundle of X, or some power of that. So it says that L prime is L twisted by n times X for some integer n. Of course, if you fix L and varying X, you just get the Abel-Jacobi map. So that's the sense in which this is a straightforward generalization of the usual Abel-Jacobi. Notice that I do have this parameter n that I have to specify, right? So the Hecke correspondence is the countable disjoint union of components, which in this abelian case is just indexed by integers. It tells you the difference, the number of elementary transforms you have to do to go from L to L prime. So it's some integer n. The analog of that in general it will be that mu that I pointed out. It's going to be a character of one of the groups or a co-character of the other. So for bigger groups, there are many ways to specify the allowed order of growth of beta. It's indexed by a dominant character mu. So it's a dominant character of the Langlands dual group or a co-character of G. So there's the entire Hecke collection, which is this infinite collection. And then for each mu, you can take that component, or you can truncate at that mu and get a finite piece of the Langlands, of the Hecke correspondence. And in some sense, those are easier because you don't have to renormalize. You can define the action, that everything is proper, compact. So, but you don't get a single operator, you get a whole collection of them. In the case of GL1, that collection is just the integers, so they're all powers of each other. Of course, they commute. An interesting feature is that they still commute with each other in the non-abelian case. So you need to say that they commute with each other at one point, but also if you do the commutation at different points. In fact, it's easier to see that they commute at different points, because you do some blow up at one point and then some blow up at the other point. Well, clearly you can change the order in which you do that. They don't talk to each other. It's trickier to see why they still commute if you do everything at one point. But if you believe in commutativity, you just, in continuity, you just bring the 2 points together. And the fact that things commute generically implies that they commute also in the special case. So you get a commutative algebra of Hecke operators. And in particular, that means that you can ask about simultaneous eigen objects, things that transform uniformly under the entire algebra. And those will be the sheaves that we want. So just another word or two to fill in. A correspondence between two varieties A, B in general is a subscheme of their product. You think a function from one to the other, or a morphism, is a correspondence that happens, such that the projection one way happens to be an isomorphism. So it's the graph of the function. But the correspondence is a more general thing. A correspondence gives you an operator on functions or d-modules or any reasonable category of objects on these things by pulling back, maybe tensoring with some kernel object upstairs and pushing down. Of course, that makes sense only if the push down is well defined. So you need one of the varieties to be compact, so the direct image, so the push down would be proper. Okay. So let's try again to say what geometric Langlands is. It says that an irreducible geolocal system on C determines a perverse sheaf on Bun. So a perverse sheaf is, well, it's a particularly nice indecomposable kind of D-module, which is a simultaneous eigensheaf for the action of all the Hecke operators. And this turns out to be the right generalization of naturality with respect to Abel-Jacobi map. And of course, there are fancier versions of the conjecture that recast this as an equivalence of derived categories of D-modules on Bun versus coherent sheaves on the modular space lock of local systems. And there are various other versions, and some of them you've already heard about, and I'm going to mention a few of them later on if I get to it. So here is the official version of the conjecture. A geolocal system on a Riemann surface is the same as or determines an automorphic D-module on the modular space of bundles. And yeah, by now all the words should be familiar. Any questions? Okay, so obviously a lot of work has been done by various mathematicians listed here, not to mention the work of Witten, Kapustin, Gukov, and so on the quantum field theory version or interpretation of those conjectures. I'm going to try to take a more explicit computational approach and try to actually prove it in some cases. So the basic idea is, well, we know how to do the abelian case. The problem is non-abelian, so let's try to abelianize it. The standard tool for abelianizing is to use Hitchin system. So we're going to use Hitchin's integrable system associated to the curve and the group. And on it, we have the twist rotation. We have the P1's worth of complex structures, some of which give me the Higgs bundles, some of which give me connections. It's a SYZ fibration in the hyperkähler sense. In the complex structure in which it parameterizes Higgs bundles, it gives you the cotangent bundles to the moduli of bundles, because the Higgs field is just a cotangent vector to moduli of bundles. So one very general approach, I would almost say a generalization of this program, amounts to homological mirror symmetry. So roughly speaking, you can take the thing that I'm sometimes calling DL, sometimes C of L, the automorphic object that you're trying to construct, has an interpretation in homological mirror symmetry as relative Floer homology between two Lagrangians in the Higgs modular space. One of them is fixed, the other is varying. So for any fixed value of the second one, you get a vector space. As it varies, it gives you a sheaf, and that's the one which, if you unravel the definitions, gives you the candidate for the Hecke eigensheaf. So you want to view L as a point of Higgs, right? L or V, I think I should have called it V, is a local system. You think of it as a point of, well, a priori of the moduli of flat connections or local systems. You do the hyperkähler rotation, it becomes a point of Higgs. It has a Fourier-Mukai dual, which is a Lagrangian in Higgs. That gives you one Lagrangian subvariety. And this is the one that's fixed. The one that varies is just a general cotangent fiber of Higgs. You fix a bundle and take the fiber above it. That's another Lagrangian. You take the Floer homology between them in some family version. It gives you a sheaf over the moduli of the second, this is not working, of the second moving object. So that is just a sheaf on Bunn, which is what you wanted to get. So there's this very general framework of deriving geometric Langlands from some appropriate version of homological mirror symmetry. Unfortunately, we don't know how to prove homological mirror symmetry, so we're not going to follow that here. So think of that just as a remark about context. Okay, so just to remind you, a Higgs bundle is a pair of V and phi, consisting of a vector bundle V, and a Higgs field phi, which is, in the case of GLN, it's just a K-valued endomorphism, and more generally, it will be a section of K tens of the adjoint bundle of V, in case you're dealing with a general group G. Hitchin studied the modular space of such Higgs bundles. We'll call it capital Higgs, or boldface Higgs, subject to an appropriate stability condition, and showed that it is an algebraically integrable system in the sense that the total space is algebraically symplectic. It admits a natural map to a particular base. The base is a vector space. The fibers, well, the generic fiber is going to be an abelian variety. In the case of GLN, it's just going to be a Jacobian of some spectral curve. There will be a more primage definition in general. That fails over the discriminant. So the generic fibers have that description, and then they degenerate as they would. So yeah, so you have some distinction between the case of GLN and other cases. However, there is a more natural description in terms of Cameral covers, which are Galois covers, whose Weil group is the Galois group. And you can give a clean description of the fibers in terms of those. In a paper from a few years ago with Tony Pantev, we formulated, our main result was a duality of Hitchin systems. So you take the Hitchin system for a group G and for the Langlands dual group GL. First of all, you get two bases, and the claim is that there is a canonical identification between those two bases. And then it says that if you work over matching points, the fiber in one is not isomorphic to the fiber of the other, but it is the dual abelian variety of the other. In other words, there's a natural Poincare type line bundle on the product, which induces a duality between them. So that's what you have away from the discriminant. There are various things you can say, at least on nice points of the discriminant, but never mind. The case of groups GLN, SLN, PGLN appeared earlier in work of Hausel and Thaddeus. In the context of hyperkähler mirror symmetry, we extended it to all group. Okay. So as I think I've already mentioned, there are two Lagrangian fibrations on the Higgs bundle. One is the Hitchin map, which goes to the base, and the other is just a projection to Bunn. And there's a little problem with the projection. It's not a morphism, it's only a rational map. The problem is with the notion of stability. Stability for a Higgs bundle involves the bundle and the field, Higgs field, while stability for a bundle involves only the bundle. So it's harder for the bundle to be stable. So you can have a stable Higgs bundle whose underlying vector bundle or principal bundle is not stable. So that's why the map is only rational. Nevertheless, you can make sense of the Hecke correspondence between them. And what we're going to do is we're going to consider the Abelianized Hecke, where instead of Bunn, I'm going to go to Higgs. So it's roughly doubling the dimensions. And I'm going to have a correspondence here which has a much more abelian flavor. And then we can talk about Abelianized Hecke eigensheaves, which will be things that behave nicely with respect to the Abelianized Hecke correspondences. And then the question is, okay, given those old results that say that yes, you can construct eigensheaves for the Abelianized Hecke, what does that buy you? What does that say in terms of the actual geometric Langlands, which is essentially non-abelian? So it's tempting to try to understand the relationship of the Abelianized version to the non-abelian result. And much of the work of Beilinson-Drinfeld and the entire school focuses on quantizing Hitchin system, which leads to the investigation of opers. One possibility that Arinkin has worked on quite a bit is to view the full geometric Langlands conjecture as some sort of a quantum statement whose classical limit is the result that Tony and I obtained in that old paper. And then the question is, can you do some sort of a step-by-step deformation, perturbation, expansion to get the full solution? And indeed, Arinkin was able, in some sense, to carry out the first-order expansion of that deformation. But it just seems to be getting to be incredibly hard. So we're looking for another approach. And what I want to describe is the possibility that the Abelianized version is, in fact, equivalent to the full geometric Langlands, not just to its zeroth-order expansion, where you use the non-abelian Hodge theory as the machine for expanding. So instead of viewing it as a perturbative expansion, you interpret it as a hyperkähler rotation. So I'm going to spend the rest of my time trying to explain that notion. So yeah, I've just said that instead of viewing the solution, the Abelianized solution as a classical limit of the full solution, it is interpreted as the value at z equals 0, where z is the hyperkähler rotation parameter of something that you need to expand for all over the entire twistor P1, but you don't have to do it. You have Hodge theory, which tells you that that exists if you just know the value at 0. So that's the basic new idea. The twistor space is fibered over the complex Z line, or Deline's lambda line. It parameterizes lambda connections, where a 0 connection is a Higgs field, a 1 connection is a connection. And the point is that we have the information at z equals 0. We want to get the interpretation at z equals 1, which we then identify as the solution of the full geometric Langlands. So let me now take a few minutes to talk about non-abelian Hodge theory. So non-abelian Hodge theory, as developed by Hitchin, Donaldson, Corlett, Simpson, Saito, Sabah, Mochizuki, and many others, establishes under appropriate assumptions the equivalence of local systems and Higgs bundles. So as I said, it's closely related to Deline's notion of a lambda connection. At lambda equals 1, we have ordinary connections. At lambda equals 0, we have Higgs bundles. So there are several different versions, but these specialization maps to z equals 0 or to z equals 1 is shown to be either diffeomorphisms or categorical equivalences, depending exactly how you set it up. So Simpson studied the projective case as well as the case of open Riemann surfaces, one-dimensional open case, about 20 years ago. But the open case in higher dimension was left open for a long time. Just a few years ago was developed by works of Saito, Sabah, Mochizuki, Yost, Yang, Tsuo, Picard, and so on. But I would say the main breakthrough is in work of Mochizuki. This higher dimensional theory produces an equivalence of parabolic local systems and parabolic Higgs bundles. I'll try to say a word about why you have to throw in parabolic structure even if you don't want to. This is quite analogous to what is obtained in the compact case, except that the objects involved are required to satisfy 3 key conditions discovered by Mochizuki, and I'm going to list them in a minute. So we're going to review these developments and outline the proposal for using non-abelian Hodge theory to construct the automorphic sheaves. And there's the obvious influence of the ideas of Witten and his school, although there will be no direct reference to them. I think I've done enough of that. Okay. So the version that Hitchin developed considers Higgs bundles and local systems and the correspondence between them. The way it's actually proved is you introduce a richer object, which you call a harmonic bundle or a twistor structure, depending on the flavor of the story that you're working out. So you introduce this notion, and it is something which contains in it enough information for a Higgs bundle and for a local system. So you can have specialization maps. And then you have to do some analysis to prove that certain maps, certain restriction maps are bijections or categorical equivalences. Something is wrong here. This is cycling back to pages I've done. Okay, so completion of these ideas depends on verification that Mochizuki's conditions are satisfied and the situations arising in geometric Langlands. Part of the issue is the difference between the moduli space and the moduli stack. Geometric Langlands lives on the stack. Hodge theory lives on spaces. You need stability. So a lot of the technical work goes into analyzing the loci of instability and showing that, yes, they cause trouble, but not too much trouble. So we'll see some instances of that. So particularly important are 2 loci, which we like to call the wobbly and the shaky locus. A bundle is wobbly if it's stable, but not very stable. There's a technical notion due to Lomon of what it means for a bundle to be, for a Higgs bundle to be very stable. And then you say that it's wobbly if it's stable, but not very stable. Roughly, it says that the nilpotent cone is not transversal to the fiber of the Hitchin map. And then there's another locus, which is the shaky locus, which is roughly the Hitchin image of bundles that are stable, but with unstable underlying bundle. And here's the definition of a very stable bundle, that a nilpotent Higgs field on it must be 0. The point is that Lomon showed that very stable implies stable, so there's a strict implication. Okay, so I've said that. How am I doing on time? 25 minutes, thank you. Okay, so here is the original version by Corlett and Simpson of the non-abelian Hodge theorem for projective manifolds. So it says X is a projective variety, smooth complex projective variety. Then there's a natural equivalence of tensor categories between finite rank C-local systems on X and finite rank semi-stable Higgs bundles on X with vanishing Chern first 2 Chern characters. So we'll call it NAH for non-abelian Hodge. Mochizuki's version, as I said, is a generalization of that to the open case. So let's go through his version. It says that, this is not working well, okay. So X is, as before, a smooth complex projective variety, but now you allow yourself a divisor D, so it's an effective divisor, which you're going to remove. So you're really going to ask the question about X minus D. Suppose that we have a closed variety Z and X of sufficiently high codimension 3 works, over which things are bad. So we allow ourselves to ignore a codimension 3 locus. such that x minus z is smooth and d minus z is a normal crossing divisor. Then there's a canonical equivalence of differential graded tensor categories, more or less as before. On the one hand side, you have finite rank, tame, parabolic C-local system with x and d. So those are the new words here. While on the other side, you see it gets longer. You get finite rank, locally abelian, tame, parabolic Higgs bundles on x mod d, which are all unstable and satisfy. You replace the Chern classes by parabolic Chern classes. So there's some slight redefinition you need. In fact, the correspondence only goes at the moment in one direction. There's some question about how much is known in the other direction, but we don't need it. So in order for this to work, Mochizuki requires three basic conditions. One is that you need to have a good compactification. The way I phrased the theorem, I started with a projective variety minus a divisor with normal crossings, except possibly on codimension 3. So there I'm already building in a good compactification. If you want to start from an open, with an arbitrary open manifold, you need to know that it has a good enough compactification so that you can get to the form that I specified. Okay, the second condition is a local condition. So the compactification is obviously a global condition. The local condition is what I was calling tameness. So for the Higgs field, it says that it's allowed to have at most logarithmic poles along this normal crossing divisor D. And there's some condition about compatibility of filtrations. I don't want to go into all the technicalities of defining exactly what the parabolic structure is, but let's just say that whatever it is, it's locally at each point isomorphic to the sum of one-dimensional pieces. Okay. And the third condition, which is again a global condition, is the vanishing of the parabolic, first and second parabolic Chern classes. So in order for Mochizuki's version of the non-abelian Hodge machine to work, you need to give yourself these three conditions for your input, and then the machine kicks in and gives you the output. A feature that is specific to the open case is captured in Mochizuki's extension theorem, which says that if U is a quasi-projective variety, and you give yourself two different compactifications, x and y, of U, where x and y are projective, reducible, and we assume that x is nice in the previous sense. So x is smooth, x minus U is a normal crossing divisor away from codimension 3. Then you can start from x, restrict to U, and take middle extension to get to y. And the claim is that this combination of restriction and middle perversity extension gives an equivalence of categories. So in that sense, as soon as you have at least one good compactification, the results you get are independent of which compactification you use, even if you then work with a bad compactification that doesn't satisfy these properties. And we're going to use exactly this delicate combination. So here's the plan. The big hope is that the known eigensheaf of the Abelianized Heckes, which is a Higgs-type object, extends by non-abelian Hodge theory to a twistor eigensheaf on Bunn for the Langlands dual group. The original Higgs sheaf appears at z equals 0, while at z equals 1, we're going to get for free the Hecke eigensheaf that's postulated. Notice that the cotangent bundle of Bunn embeds as a Zariski open subset of the Higgs moduli space. And as I keep emphasizing, it's not the whole thing because of the existence of Higgs bundles that are stable, but whose underlying bundle is not stable. So you only get the ones whose underlying bundle is stable. If we ignore stability, or if we work at the Stacky level, then the two are exactly equal. Whoops. Okay. So the heart of the matter amounts to verification of Mochizuki conditions, and here is the detailed plan. So we start with G-local system. Let's pretend it's V. Then V is a vector bundle, and nabla is a connection. Or in general, V is a bundle, and nabla is a flat connection on it. And it lives over the curve, say. First step, I use hyperkähler rotation on the curve. So this is a classical operation to convert that to a G Higgs bundle, E theta, on C. So this is just a hyperkähler rotation underlying the Hitchin system itself. So that's Collette-Simpson on the non-abelian Hodge correspondence. Okay. Next step. From this information, we build a Hecke eigensheaf, well, an eigensheaf of the Abelianized Hecke correspondence living on the Higgs moduli space. This is what I did in the Inventiones paper with Tony. So that's taken care of. So this functor sends an E and a theta, which is a Higgs bundle, to a Fourier-Mukai transform of, you think of E theta as a point of the Higgs moduli space. You convert it to the structure sheaf of that point. You do Fourier-Mukai to that sheaf, you get a new sheaf on the dual space, which just involves putting a Langlands dual group there. And you can describe it exactly. I don't really need to do it now. So, but basically I'm converting something that lives at one point in the Higgs space to something that lives on an entire fiber over the Langlands dual point. That's what the effect of Fourier-Mukai. Okay, so that's the second step. The next step is to convert that to a parabolic Higgs sheaf on Bunn. So I have a sheaf that happens to be a Hecke eigensheaf on L Higgs, and I want to go from that to Bunn and make sure that it satisfies Mochizuki's conditions 1, 2, and 3. That is the part that takes all the work. Assuming we can get that done, the next step is to convert the parabolic Higgs sheaf on Bunn to a parabolic local system on Bunn. This is the parabolic version of non-abelian Hodge correspondence due to Mochizuki. Once we have something satisfying its three conditions, we use the one direction that's proven of his correspondence to go back from a Higgs sheaf to a local system. So we get a local system on, it's really local system on a Zariski open subset. You can think of it as a perverse sheaf. We'll get to that in a second. So we're applying the first Mochizuki theorem not to the projective variety, but to the smooth proper Deligne-Mumford stack on a projective moduli space. You have to check that Mochizuki's proof works in that slight extension. The next step is to convert this local system, parabolic local system, into an ordinary local system on a Zariski open subset. Just throw away the locus where you have parabolic structure. So that's just restriction to a Zariski open subset. And finally, step 6, we want to cache in, convert the ordinary local system on the Zariski open subset to a D module on Bunn. And that's done by Mochizuki's extension theorem. Maybe I'm not saying that here, but this is exactly the setting to which Mochizuki's extension theorem works. So start arg. So starting in at the end of step 4 here, doing 5 and 6 amounts to, we have one compactification, which we don't like. We restrict to a Zariski open subset on which everything is nice, and then we extend the other way using Mochizuki's extension theorem. So modulo a lot of details. All the other steps in this program have been taken care of. Let me go through this one more time. So number 1 is Collette-Simpson. Number 2 is essentially a Fourier-Mukai transform. That's what's in the published paper. Step 3 is the one I'm skipping. Step 4 is the parabolic non-abelian version of the non-abelian Hodge correspondence. And then 5 and 6 together, as I was saying, are restriction and middle extension functors. So that's exactly the setting for Mochizuki's extension theorem. So in a paper from December, together with Tony Pantev and Carlos Simpson, we study general operations on the category of Higgs bundles, but in particular the direct image. That's the operation that causes trouble. Natural operations such as pullback and direct image with respect to homomorphism are well defined in the world of harmonic bundles and in the world of local systems, or D-modules. It's less obvious how to define them in the world of Higgs bundles. You need to, I mean, it's clear that you need to do some sort of causal resolution and take cohomology of that. But the exact version of how to do it has never been worked out. So the point is, you know in principle that it can be done because it can be done for local systems. Local systems are equivalent to harmonic bundles, and harmonic bundles are equivalent to Higgs bundles. So through the machinery of non-abelian Hodge theory, you know that there is such a functor. But can you write it down explicitly? And that's what we needed to do. So we write down an algebraic formula for the direct image for Higgs bundles under some hypotheses. The case where the map is to a point, in other words, where we just take global sections, was worked by Steve Zucker a long time ago. And of course, our proof uses heavily all of Mochizuki's machinery, together with a comparison between R modules, which is Sabar's language, and parabolic modules. In good situations, this formula allows us to compute the Chern classes of the parabolic Higgs sheaves on Bunn, which is one of the three Mochizuki conditions that we need to satisfy. So this is essentially the missing step number 3 in the diagram. So as unfortunately, at this point, we can do the analysis only under fairly restrictive conditions. We can do it for a family of curves. So the base can have any dimension, but the map from X to Y needs to have one-dimensional fibers. This is sufficient if you're dealing with a group like SL2, where the fibers of the Hecke correspondence are curves. Why are they curves? Because you give yourself a rank 2, an SL2 bundle, and a point, and you're asking what are all the ways of possibly making a minimal modification at the one point? Well, they're just parameterized by all the lines through that point, through the origin in the two-dimensional vector space. So they're parameterized by a P1. So generically, the map we have is a P1 bundle. In fact, it's more like a conic bundle and has many degenerations. But so in the case of SL2, our theorem applies. It will need to be generalized to higher dimensions in order to work for other groups. So I guess that's probably enough. There's a second paper coming up, hopefully soon, with Pantev, where we take one concrete example and work out completely all the data. So the case of P1 with 4 marked points has been worked out by Arinkin and Lysenko. And so the case of P1 with 5 or more points is unknown. So I think we can do it for P1 with any number of points, but we focus on the case of 5 points. There the moduli space is, well, I mean, it has various pieces you can pull off, but the basic moduli space Bunn, after you peel off all the abelian pieces, is two-dimensional. In fact, we can describe it as a Del Pezzo surface. It's the blow-up of P2 at 5 points, which somehow remember the 5 marked points that you had here. So there's a concrete model, and we do the analysis, and we write out explicitly the Hecke eigensheaves in the case of SL2 on that curve. So that's going to appear soon. So thank you, and see you all next year. And don't applaud yet, because Ugri has asked me to make a little announcement. As you see, there's these 5 famous Japanese people. Don't ask me how I got in the list, who are preparing the String Math 2018. We already have dates, location. It's in northern Japan. at Tohoku University, which for mathematicians, for algebraic geometers, probably the only thing they know about it is that there's a Grothendieck paper in the Tohoku journal. But it will exist, and that's where the next string math meeting is going to be. It's sponsored by the Tohoku Forum of Creativity. And just in case you have an extra week to spend after that, the week after that will be String 2018 in Okinawa. Thank you.